Welcome everyone to the last Simon's lecture of this year. It's good to see so many of you here. And today Lenka will tell us about some research just out this. Or very new. Not even.
Thank you very much for still coming, even to the third one. I hope that means that you're enjoying it and that you will enjoy also today. So this is part 3 of looking at computation through the lens of spin glasses. And I already anticipated yesterday what we will do. So yesterday, we were looking at learning with very simple neural networks, and all those we were looking at were feed-forward architectures. But since about 2 years, the world is crazy about transformers and large language models. So can we say something about those? So, I mean, of course, we need to start somewhere. So starting somewhere, it will be extremely simplified, but it's a start. So just to kind of explain a little bit what this is. So in the same sense as a fully connected layer in the neural network, as we saw yesterday, is just the multiplication of a matrix. So it takes a vector in d dimensions and brings it to a vector in, say, d 2 dimensions, some other dimension, right? So it's a mapping from one dimension to another. And a attention layer of which transformers are built is also just the mapping from one space to another. But this time, so again, there will be dimension of the kind of input, dimension of the output, but they are not only vectors, they are actually sequences of vectors. So L, think of L like the length of the sentence. So we are transferring matrices that are size L times D at the input. That will be the X here. It's a vector of d dimensions, and the J indices and I indices, those are indices for something that goes from 1 to L. So there's numbering the words in the sentence. And D is the embedding dimension of how many bits we actually need to represent the word as a vector. And then this can be mapping to a vector Z that can have different dimensions, so dv, that doesn't have to be the same, but has the same length L, so the length of the sentence stays. And then the mapping that the transformer is using is also multiplication by a matrix, but this time there are 2 matrices, since the X itself has the length index and also the embedding index. So there is this WV, that's the value matrix, that has size capital L times capital L. No, sorry, WV has, so A has the size. A is the attention matrix, and that has the size capital L times capital L. And WV, that's a matrix that has the size the embedding dimension of X on one side and the embedding dimension of Z on the other side. So in my notation, D and dV. So again, these are 2 matrices, but since there are 2 indices, one needs to be careful about the indices. And now this A is an attention matrix, and in some, say, like simplified model of a transformer, this could be the elements of the WV, they are all trained. And in some simplified models, the elements of this attention matrix could maybe also be all free and trained. But that's not what's typically done. That's not what's typically done in the current architectures. What's typically done is this: the matrix, the attention matrix A, takes a particular form like this, that itself actually depends on the input X. And there are 2 additional matrices. This one is called key and this one is called query. They all have the dimension that is on one side the embedding dimension, and on the other side some other dimension, some dk or dq that need to be equal, because then we make a dot product between them and normalize this way, and this is called a softmax function. And this is how people do it. Okay, why particularly this way? Okay, that is a good question. But our goal was kind of, can we now study learning? And what is learned are all these W matrices. Can we now study some toy model where these Ws are learned that have this form and not the fully connected form? And can we extract something interesting from it? Right, so then, okay, this is one single layer, single head, attention. And now, you know, when people explain to you transformers, they typically show you a picture like that, where what I showed is part of the orange box. Okay, so they show you these boxes. These blue boxes are the feed-forward, are the fully connected layers. Orange boxes are the attention layers. Yellow boxes are some kind of normalizations and additions. And then just from these boxes, and then these connections are skip connections between the layer. From these boxes, you're supposed to understand what it does. This to me seems completely crazy. I don't know why people show these type of images. But the previous one, there was kind of all the matrices and dimensions, and all you need to actually know what is there was written on the previous slide. This is not my slide. I just typed transformer on Google and took like first image that had this architecture. So I should actually probably give credit to someone. I don't know who. So now what can we hope to to understand here? Well, you maybe kind of anticipate, since most of you probably were at the previous 2 lectures and we talked a lot about phase transitions. And in large language models, there is this craze about abilities that emerge. So things like understanding a certain language, like Persian question and answers, or modulo arithmetics, I think that's what it means. These are just some properties that the large language model somehow suddenly, as the model gets larger and larger, starts to be able to do. And this is called emergence, and it's not kind of clear what's the actual status, right? Because one kind of changes one parameter, the model scale, but this can be, of course, increased in zillion different ways. One can increase number of layers, the embedding dimensions, the number of heads, many other things. So which ones and how will it depend on that? So these are, of course, good questions, not really properly studied, because training each case, so to see something like that is expensive. So there is still a lot of things to do. But okay, there is this idea of emergence. In physics, if something emerges, it's the phase transitions in the large size limit. So can we get a phase transition in a model of A attention? That's a natural question. And that's what we asked in this paper that came out a few months ago. And just, I don't know if it is good to brag about Twitter, but I am active on Twitter, and this paper, from papers that I ever posted, this one attracted the most attention. The only other tweet that attracted more attention is the blackboard from my machine learning lecture that has like 3 floors and is 15 meters wide, and I have a screenshot from the recording of the lecture, and I'm tiny in front of the blackboard where I explain linear regression or something like that. So that one was more popular. This is the second more popular, up to the point that this guy Cody or on AI, that is really nice, kind of a YouTube channel, made a post about it where, yeah, he totally exaggerates what's actually in that paper. I was thinking, yeah, that I should transcribe it and send it to some grant agency. I would not dare, like myself, say these things, but it was very funny listening to it. So what did we do? Okay, let's go back to. So as I anticipate, we simplified things enormously, but along similar lines as what we have seen yesterday and the day before. So first of all, we have a synthetic model for the data. So our inputs are random IID matrices, random sentences, but all the elements are just Gaussian numbers of a given variance. The sentences have length L and embedding dimension D, as we kind of introduced these numbers before. Now, what is the function is what is non-trivial. So we are mapping this X to Y. So we will be looking at supervised learning here. So the teacher in the language of yesterday. And what we do, we take the X, and then we have 3 other numbers here, omega, A, and Q, that will be drawn again at random in a certain way, and they are representing the ground truth relation between the X and the Y. So the omega will be some kind of a strength of how much things depend on a position. A will be a matrix that is L times L, and that will be telling us how much kind of the position in the L direction matters for the output. And Q, see, this is the softmax, so this is a bit like the dot product. In the dot product, we usually have Q and query, so we just say, okay, let's simplify, make Q equal to query. So we tie those 2 weights, and we take this Q that multiplies X, so that's kind of some like kind of ground truth semantic meaning that matters for the label. So Q will be the semantics and A will be the position, just to introduce these two words. And then the student, what is the neural network that we are actually training? That is a single layer, single head attention, where the value matrix here is missing, it's equal to identity. The key and query are equal again, and key and query will be the only things that are trainable, so that the loss then depends on this Q. Here we have the X, the signal. We add to it a position, and it's some vector that depends on where we are in the sentence. So we will be considering the case, simplest case, we consider L equal 2. So our positions is just like +1 vector or -1 vector. This is imposed and known. This is not learned in our case. And that's it. So it's a dot product. Value is 1, Q and query are tight. And right, that's it. So that's the model. And now, you're wondering, okay, this still looks complicated. So for this model, we can actually now unroll the methodology that I was using for the past 2 lectures and study what? The global minima of this loss. Okay, so not yet kind of gradient descent dynamics, but we can study where the global minima of this loss are and what they are actually telling us about what was learned. So we leave the question whether these global minima are actually achieved or not open, but we can look where they are. And these are the equations that one needs to write and solve. So the limit in which we work is important. We take the number of samples, we take the dimension, the embedding dimension and the number of samples large and proportional to each other, similarly as yesterday, and the length of the sentence constant. So that's the limit in which we know how to write equations that are not high dimensional anymore, that just have number of parameters that is some small constant times L. They look like this. And from them we can extract our favorite phase diagrams. So what is plotted here? First of all, the x-axis is alpha, the number of samples over dimension. So the more samples, the more kind of we know, the easier the task should be. And what is plotted is what I call order parameters. So one of them, so I look at the global minimizer, I look at the global minimizer of the loss, I call it Q hat. And then I look at the correlation between the Q hat and the position P that I imposed. And that's one order parameter. And I also look at the correlation between the Q hat and the Q star, the ground truth Q that mattered to create my actual labels. And that's my other order parameter. And what I see is that as a function of alpha, there is a point where, for smaller number of samples, it's a point where this positional order parameter M is positive and the semantic one is 0, and above which is the other way around, where the positional is close to 0 and the semantic is positive. So to interpret it back, thinking kind of language models and sentences, if we have enough samples above certain well-defined threshold in that limit, then we start to be using the semantics and not the position. And before that, we are only using the position in the sentence and not the semantics. So that's what kind of pops up in this model. And when we can also extract from the same equations the test mean square error. It's a supervised problem, and it looks like so. Again, at the phase transition, it has a sharp jump to something better. As we start using the semantics, we start being able to predict better the outputs. So here, this is just a plot how, because what I didn't say here is that this is for fixed values of this A matrix and omega that pops up. I have it reminded here. This was, again, I'm reminding here the function that I used to generate the labels. So it depended on a fixed matrix A and a fixed matrix omega, a fixed scalar omega. And omega was parameterizing how much I'm using the positional information to generate my labels. And when I look how the phase transition shifts when omega changes, like the more position is used in the ground truth, the higher number of samples is actually needed to start using the semantics. So this would kind of make sense, like the more positional is the ground truth, the larger region, this is actually the right fixed point. So we can extract things like that. And this is just the beginning. This model and the fact that we can solve it and look at the global minimizers and also the training dynamics of the gradient descent. It's a point here. We haven't done it yet. It's a playground to investigate what's happening in the learning with a dot product attention layer. And it's interesting to look at the role of the nonlinearity, for instance. We use the softmax. There are many other works that use linear transformers. I don't even know whether that actually is a bad thing here, whether that actually makes things worse or not. This we can investigate, the role of the skip connections. We can add the learnable readout layer as they are there in the actual architectures. We can do multiple layers here. That's quite interesting. We can look at the dynamics of the gradient descent, the role of the structure of data. That's also something that the theory is kind of flexible and can take into account. And hopefully maybe start thinking about things like what is there beyond dot product attention and why really dot product attention really? Like I don't know. I mean, I read the reasons people give, but I'm not really happy or convinced. So I cannot say that I understand. So that's this part about our recent work on transformers. And when I actually go on, it stops. Because the second part of the talk had slides of different formats, and I was too lazy to kind of make them the same format. So let's continue. Let's continue. And it's also, it's quite a different topic. So the transformers, that's more like a continuation of yesterday's lecture along the lines. We were questioning all the assumptions, and one assumption was fully connected layers. Now these dot product attention layers seem to be the state of the art, so we need to study them and understand what's going on with them. But now I go into this topic of optimization of incomplex landscapes that I also kind of promised, already made some remarks about things. So let's go to that. So now this is a lecture where we look at computation through the lens of spin glasses. So when we say non-convex complex landscapes, this will be the landscape of the spin glass. That's kind of our canonical example where we like to think about how things behave and kind of wishful think that this is generalizing to other interesting cases, which may of course be the case sometimes, not all the time, etc. So this is how the landscape, this Hamiltonian, a function of x looks like. Now the x is usually either binary or living on a sphere, that depends. And then the p over there is usually 2. In the examples we talked about, it was 2. Or sometimes it is bigger than 2. And there has been really interesting progress recently with actually also people who are sitting in the audience, where we understand, I would say now, that what is the best polynomial algorithm and to what cost it goes in this type of landscape. And this started with works by Subak and Montanari, and then on the various versions of this model, then in the Ising P-spin, a really kind of nice pair of works in which, where is Mark? He's somewhere here. He was involved in both, and Bryce is also somewhere over there. Okay. And Bryce is not here today? I don't know. Over there. Okay, great. And okay, so this is really, really nice progress. I have nothing kind of to add to it. But what I want to ask is another natural question. To what cost do simple algorithms go? Right? Because yesterday we were talking about machine learning, and everybody in the computer science department who studies machine learning cares about gradient descent. I may come to them and say, oh, look, in some simplified setting, my approximate message passing is optimal. Most of them will not care, right? Especially those that collapse my wave functions into either physics or mathematics. They will not care about me studying other algorithms than gradient descent. Okay, so it happened to me so many times that I say, okay, maybe they are somehow, they are right. Maybe we should keep looking at simple algorithms, and still we need to understand what they are doing, right? So this is a question that for the spin glass was a bit neglected, because maybe we were a bit too obsessed to be optimal and all that, but it's a very natural question, right? So we define a very simple dynamics and we ask where it goes. Okay, and can we analyze it? So for the gradient descent, it's something that I did not really cover yesterday, but there is this beautiful construction called dynamic mean field theory that, it's kind of a word that may scare you, but it's really nothing else than doing what we were doing before, writing probability distributions and analyzing them with some kind of message passing algorithms or its forms, but not doing it directly on the variables, but doing it on short trajectories of these variables. Also, this just makes our variables typically not scalar, but vectorial. But we know how to deal with vectorial variables, so this is not a big deal. It's kind of included there in the overall structure that leads to these results. And it's really nothing more what the dynamic mean field theory is doing. And in physics, it has been there since maybe 30, 40 years that people were using it. Sometimes it went under the name Coulomb-Dollo-Kurchan equations. Some people here know that. And again, recently there has been really cool progress of actually using all this methodology of state evolution of approximate message passing to actually prove that this is correct, that this, under the assumptions of these models, this is the right thing to do. And that started with this work from Andreas' group. And when Cedric Gerbelot realized that you can prove it this way, this group of people we were working on different variants of the DMFT, including stochastic gradient descent and discrete steps and momentum and various kinds of accelerations. And once Cedric understood Andreas' proof, he actually generalized it and also simplified to all those variants. So now we have like a very generic proof for very generic case. So the bottom line here, this is a powerful method when something interesting happens in just a few steps, right? The trajectories cannot be too long because we need to be summing over all the trajectories of the neighbors, and this will not be possible if they are too long. So the trajectories need to be short. And when they are, we can do things. And I was talking earlier today with Elhanan's groups about, for instance, this paper where we just need to look at two steps. This is just a comment for those of you who actually know about these papers about information exponents and leap exponents and staircase property. So with DMFT, we can show that reusing the samples and using only two steps of gradient descent, some of the functions like the x power 3 minus 1 that are hard to learn in one pass gradient descent are actually not hard to learn with the multi-pass gradient descent. One pass doesn't learn anything. Multi-pass already in the second step starts getting correlation. So things like that you can extract from the dynamic mean field theory. But I really want to stop to talk about how that works. Go back to the spin glasses. But we will do something similar. So we will be looking at the Sherrington-Kirkpatrick model where the graph of interactions is fully connected, and we need to rescale properly the j's so that this kind of behaves nicely. It has a proper limit, that the limit makes sense. And also random regular graphs where the graph is random regular graph, and then the spins, in both cases, the spins, the axis will be binary variables. In the first case, the j's as well, but in the first case they are rescaled, and in this case they are not. So this will be our landscapes, and we will be looking what's happening. So these landscapes have been studied in many papers. Here I really just cite roughly 3 papers, but there are like 300. So we know a lot about the equilibrium. Equilibrium meaning that we study the properties of the probability measure above for generic values of beta. And that's in the Sherrington-Kirkpatrick model. Giorgio Parisi computed the lowest energy of that landscape that has that value, and also characterized that below a value that is -half, something very tricky called replica symmetry breaking happens. And the work he did stemming of that led then to his Nobel Prize, and Michel Talleyrand, who also got the Abel Prize quite recently. I know him because a lot of the math that he developed, he used it to study exactly that Boltzmann measure and established Parisi's results rigorously, or large part of them. And then there is a big line of work that I am not putting. On random graphs, it's a bit more complicated, at least from the mathematical point of view, but we do have a prescription for where the replica symmetry breaking happens and at least a numerical population dynamic procedure to compute the ground state energy. So this has been studied a lot and we know a lot. Now the question is, what about the dynamics? So first of all, which dynamics? The one I will be talking about, something simple. So we will be just walking in the space of configurations, in these 2 to the n configurations, and we will be updating each x at every time. So we have discrete times, and then every time each x will be updated based on some function of itself and its neighbors. And that's it. So it's a local dynamics, synchronous, deterministic. This function fi is deterministic. And our theory will be valid for all those. It can depend on the node I, that's fine. So an example that is natural is what in physics we call the global dynamics at 0 temperature. Now, maybe to explain it, if you are looking at the case where the Jijs would actually be all ones, they don't need to be randomly plus minus 1. We also include the case where they be all ones. This is just the majority dynamics, right? Here I'm just counting how many neighbors are up and how many neighbors are down. And then I turn in the sign of the majority. Or I stay what I was if I don't have majority around me. So that's a very natural dynamics. And now where Jijs are random, well, we kind of reweight this x. It's a reweighted majority. Right? So it's a very natural dynamics. I explained it to some journalists. Okay, if my friends want to buy iPhone, I want to buy iPhone. If my friends don't want to buy iPhone, I don't want to buy iPhone. Every time step I change my mind. Where do I go? Where does the graph go? Right, so that's the dynamics we are going after. And not much is known about it. So what is known about it since a long time is counting fixed points of this dynamics. So configurations so that if you apply the dynamics on it, you stay where you are. So that's quite at least in the physics literature, quite well-known paper by Bray and Moore, where they plot how many fixed points there are as a function of the energy, the value of this h that I defined. And there is this full line where it is correct, and the dashed where it's where their calculation, they say, okay, we don't know, it's probably not correct. And then we know, well, we have this incremental AMP since recently that provably gets us to the ground state energy, to configurations that have the same energy as the ground state. And there is also this folklore conjecture in statistical physics that the simulated annealing algorithm does the same. But that's very hard to analyze. So as far as I know, we don't know how to analyze that, even non-rigorously. So the question is natural, to which of the minima do the other algorithms go? So for instance, this 0 temperature quench, this majority dynamics that I defined. Okay, so to get to what we know about that question, I need to start a bit, I will start with the fixed points. But I will define a more general notion of a fixed point, which we call h-stable local minima. So it's defined above there. So configuration x is h-stable local minima if the equation over there is true for a certain h. And this is kind of enforcing a stability. So if h is 0, these are just all the local minima. But if h is positive, these are the local minima that are stable, that have an additional margin. And in combinatorics, these have been studied actually under different names. So either they were called assortative partitions or friendly bisections or disassortative partitions. I'm not specifying what the Jij is. So mainly I will be interested in 3 choices of Jij. Either all of them are 1, either all of them are -1, or they are ±1 randomly. And all the 3 are interesting, and depending which one I take, this problem has different names. And I just really cite here one paper because that's the one that Afonso Bandeira pointed to me and asked whether we cannot solve something like that with the StatFis methods. And so that's the one that inspired us studying this. So let's start with the questions of how many of these h-stable configurations there are, and can efficient algorithms find them. So this is really a vanilla problem for the belief propagation. This project actually started 3 years ago when the other authors of the paper, but me, were actually students in my class, and this was a class project. This was an exercise. Back then, I didn't know this problem is actually like so interesting as it turned out being. So this was a natural question that we could solve, and this was like a project in the class. With the equations that we derive in the class, we kind of write, what it means to be a H-stable local minima via a probability distribution written above. Then we realize that if we naively draw a graphical model corresponding to this, this will have a lot of short loops. So we need to make a trick where we copy the variables on the edges and add additional constraints of consistency between the different copies variables. And this creates a graphical model representing the same probability distribution, but in a way that is locally tree-like. Now, once it is locally tree-like, we can enroll the belief propagation. We have a good reason to believe that it will actually work. And it's just we use the recipe of what it means to do belief propagation, write it down, and evaluate what's going on. That's what we did. And we found for D regular graphs, depending on the value of H, we characterized when these H-stable minima exist and when they don't exist. And this is summarized in the table. When the degree goes large, there is a particular scaling to which it converges, which actually was a number known in some old physics papers with some slightly different motivation of getting to it. That's interesting. I actually found out this paper by Googling this number. So it's just to give you a tip. It's actually tricky. You cannot Google this number. I needed to Google twice this number because there is a factor 2 between our definition of the Hamiltonian and theirs. And I figured out, oh, maybe there is this factor 2. I should also Google twice this number. And that's how I found that their paper, never mind. And then we found, so we characterized this. This is what we were expecting that we will manage. But immediately we realized something interesting that we were not expecting, but it is not complicated. And that's whenever this H is positive, that the way the solutions are organized is what we call the frozen 1RSB. They're isolated from each other. If there is a solution, then there is no other solution to extensive distance from the solution. And for somewhat trivial reasons in this problem, the proof takes 10 lines. It's really simple. So I don't have now my statue. So this is a toy version of this little statue that I just got. And what that implies, again, by works of people in the audience, that this actually makes the problem for positive H computationally hard for local algorithms, but probably much larger class of algorithms. And also what we saw in our equations, that actually the form of the final equations totally does not depend on the fact whether I take the Jij's all positive ferromagnet, all negative antiferromagnet, or plus minus 1 randomly the spin glass. So these assortative or disassortative partitions, or the max cuts and the min bisections, or the spin glass versions of that, they all kind of behave the same on these regular graphs. So there is this universality, which again is known implicitly in the spin glass literature, but was not at all anticipated in the mathematical literature. In mathematical literature, by this time, these versions were treated separately with no connection whatsoever made among them as far as I saw. So then what we did is that David came to visit us in Lausanne, and we realized that we can actually prove quite a bit of things about this problem rigorously in the limit of large degree. And this is a summary of what we managed. So in the limit of large degree, we need to rescale this capital H to a small h so that, again, the limit exists and makes sense. And we managed to prove this threshold of H star, that this time I write it twice that number, that actually is the threshold for above which these H-stable minima do not exist and below which they exist. And concurrently, there was a work of, in my understanding, students here in MIT that did something very related with a different method, and that it was very interesting. We also managed to prove the universality to a large extent. So that's to my knowledge, kind of a first work where we connect these three different kind of worlds that so far we're living disconnected. It says, look, it's all the same thing. And okay, the computational hardness, I listed it here. We did not really considerably contribute to it. This was still a conjecture, but I learned this week that, again, people in the audience are working on making that a theorem, which is really cool. So there is this so far conjecture that for positive threshold H, it's computationally hard to find these gapped stable states. It will stay a conjecture, but it will be a theorem under some assumption on the class of algorithms for which it is true, if I understand pretty soon. And then the kind of last figure in the paper was this figure that looks a bit charged, but that I found very interesting. So let me walk through the figure. So the y-axis is the energy, so the cost. I know how high are we in our landscape. And the x-axis is this margin h. So h0 is the canonical case where we are just looking at any local minima, and h positive are these gapped or stable minima. And now the two black lines, there's the ground state energy. You just have nothing below that. And the ERSB, that's where the equilibrium measure becomes replica symmetry broken, so ultrametric, complicated. If you sample uniformly over all configurations at that energy, it becomes very complicated, and Parisi and Talagrand and others describe the structure in which way it is complicated. Now, above the green line, so I should say below the green line, the calculation that we did, which is annealed, is just the first moment, we cannot show anything about it. So below green line, we know nothing. But above the green line, the second moment matches the first moment. And using that, we can show what is the maximum energy that is achievable. And in this region also, what is the minimum energy of these H-stable fixed points that is achievable. So that's what this picture means. And what is remarkable here is that I say that there are frozen islands of roughly uncorrelated configurations, these H-stable minima, because if the annealed calculation is correct, it means that they are roughly uncorrelated. And they are kind of diving in the sea of all the configurations at that energy that has this full-step replica symmetry breaking structure that cannot at all be described by something like an annealed calculation. They are very correlated. It's kind of very complicated. So I find it remarkable and somewhat unexpected that this actually happens, that you have the equilibrium that is complicated, yet when you ask about minima, they are organized in a way that is essentially uncorrelated and is described by the just first moment calculation. To me, this is, I mean, I don't see like why, of course it can be true since it is true, but it's definitely surprising. Okay, let's go back to the dynamics. So this is just redefining, this is just showing, this is again just the dynamics, and for simplicity, concreteness, not simplicity, the theory is generic, but for concreteness, we will be looking at this majority dynamics. And the questions are now, to what of the minima it actually goes. So far, we just described how many of them there are at given energy and all that. We still didn't say anything about where it goes. Does it even go to a fixed point, actually? Because even that is not, in general, true. But if it goes to a fixed point, at what energy? So let's just think about the dynamics a little bit on this picture. So what this picture actually is the configurational space for a graph that is drawn here. So it's a graph with 12 nodes with these edges. Okay, it's a graph. And what is here is the 2 to the 12 points. So you need to trust me that there are 2 to the 12 points. Okay. And the way they are connected is that if from one of the configurations that dynamics leads you to the other, you put an edge. Okay, so the edges are the edges in the configurational space. And now they are colored. The light blue ones are the fixed points, and the dark blue ones are the configurations that lead to a fixed point. The red ones are attractors of length 2, so you're just switching between two configurations. And the orange ones are those that lead you to an attractor of a length 2. And all the configurations are drawn. So what I described, this is just a zoom on one of those kind of bases of attractions of one fixed point and one particle attractor. And what we know, and we can in an elementary way prove, is that for this dynamics, we can only have fixed points and limit cycles of length 2. Nothing else is possible. For more complicated dynamics, we can have limit cycles of arbitrary up to exponential length. But for this particular one, 1 or 2 is the only ones we can get. And we can also, since we can count fixed points, we can also count the cycles, the stable cycles. And this actually is a work a few years back, again, with some motivation in neuroscience, but formally they did the same calculation. And now the method that we introduced that we call backtracking dynamical cavity method, it combines the idea of the dynamical mean field theory, taking the trajectories from my variables, with this very simple trick of not going from the initialization forward, as the DMFT usually does, but going from the fixed point backward. And that's why we call it backtracking. And that's it. By doing that, we can count how many points there are that are at most p steps away from an attractor. And we can condition whether this is a fixed point or whether this is a cycle 2 attractor. And that's what we do. And now, okay, from what I told you, it's almost self-obvious that this, again, is a constraint or a setting for which I can readily apply the belief propagation for the same reasons. Now just my variables are a bit more complicated. Now there are these length p plus c, where c is the length of the attractor, p is the trajectory to get to the attractor. And I write a probability distribution that is just collecting all the consistency constraints, such as at time t plus 1, I need to be consistent with the fact that at time t, I was in a configuration from which I went to the next one by the dynamics that I'm considering. So that's what's written here. And I also need to be constraining that indeed at the end I am at a cycle, so this needs to be true. And I can also add terms that are looking at what energy I am, at what magnetization I am, at what observable, whichever observable I want, in the usual way that we do it with the Legendre transformation. That's kind of the core of statistical physics, like how we get from energy to entropy and temperature. That's kind of the generic procedure that we do here. We need to do, again, this same trick. Now this becomes a bit bulky, this same trick of copying these trajectory variables on the edges so that the underlying graphical model becomes locally tree-like, just as we did to count the fixed points to start with. And then we get the final equations that have this form. They don't look particularly transparent, especially because there is this little a and the big A in which I hide all the constraints that one actually needs to kind of write explicitly if one wants to solve them. And solving them takes, as I was anticipating, number of steps that is 2 to the length of the trajectory. So I cannot deal with very long trajectories, but 2 to the 10 is only 1,000, so I can sum over 1,000 numbers. That's not such a big deal. So I can do short trajectories. And what do I get for this dynamics? Still the same one. A priori, it's not clear that I will get something in 10 steps. But that's where the surprise came. So here the numbers I'm showing you are for 4 regular graphs, and I'm conditioning to go to a fixed point, not to a cycle. And what I'm drawing in the first column is the length of the trajectory, so this p, how many steps I go. And the second column is what is the entropy of configuration that I cover by that divided by log 2, because I have 2 to the n configurations, so that's the most I can get. And you see how incredibly fast this converges to 1. So when we did that first in that class, and the student that was working on it brought me these numbers, as a physicist, I know that log 2 is 0.69. Okay, I don't know if mathematicians also know that log 2 is 0.69. Who knows that log 2 is 0.69? Some of you do. Great, awesome. So right, the student it did not strike her, but when she brought me the number, I was like, oh my God, this is everything. And this is not taken for granted, because one could think that 7 steps back, you still cover almost nobody. And so we were very surprised by that, but positively so, because that means that it's very reasonable to conjecture that once the entropy is 1 up to 4 digits, of course, still almost everybody is elsewhere, right? These are logarithms of exponentially large numbers. but like, how could it be that random configuration goes somewhere else? Like, this would make no sense. So for all kind of physics, common sense reasons, this just must be covering the initial configurations. Although this is like a big step. Proving something like that, good luck. Because I think some of you will be interested to prove that. But to me, that one will have to do some gymnastics to kind of get over that. So, and what is the third column now that we realize that? That's actually the energy of the attractor to which we go for random such configurations. So if this is going to 1, this must be going to the energy to which the random initialization goes. And indeed, when we actually do the numerics, that's what we see. And we can also do the dynamical cavity method forward, not backward. And we also see that it a little bit slower, but also pretty fast, converges to, similarly looking numbers. So say, the 3 digits and the 4th one partially is the right number here. And to get more, well, we would have to sum over 2 to the more and, solve these fixed point equations. So that's probably doable, but maybe not worth it beyond this. So we were quite happy about that. And an interesting thing that we noticed is when we actually look, this is just some zoology of the numbers, right? But for different degrees of the graphs, for the degree 4 graph, the energy to which this quench goes is above the energy at which the replica symmetry breaking happens. And honestly, that's what I would expect. I would expect you get stuck really fast, and then below, kind of you need Parisi to explain you what happens. But when the degree grows, it's actually reversing, and this greedy quench goes lower than where the equilibrium measure becomes complicated. That's kind of strange again. It's a similar strangeness to what I already said, that you have this like n-yield calculation in the full RSBC. Also, the dynamics goes to the full RSBC. Okay. And I'm only showing you even degree because for odd degree, we actually go to a cycle from random initialization, and we see that in the equations. So we need to do something else for odd degrees. Another thing that we can readily get from this kind of calculation is actually ask if just we think about the ferromagnetic case, so really the majority dynamics. If we start almost everybody wanting to buy an iPhone, by this dynamics, in few steps, everybody will buy iPhone, clearly. If we start at random, it's actually known, and it's confirmed by this calculation, say for odd degree, this is true, for that we will go to a cycle. So we will not converge, my opinion. So some people will stay with their opinion, but the linear fraction of people will just every time switch their opinion, and they will keep doing that forever. So that's if we start at random. But if we start somewhere in between, say 80% people want to buy the iPhone, will we go to consensus or will we oscillate? If 60% people want to buy, will we go to consensus or oscillate? There is a phase transition above which we go to consensus and below which we oscillate. This is a known phase transition that people are not known. It's known that something like that on one side you go to consensus, on the other side you don't. And there are papers studying upper bounding and lower bounding this transition. It's interesting whether there is a transition, whether it is sharp, etc. And what we do predicts that indeed there is one. And by changing the initial magnetization that we can very readily in the equations by this Legendre parameter, that's really a simple change, we can actually locate at what value of the initial magnetization this phase transition is. And it is somewhere at 0.7875, which is consistent with numerics, and this is kind of the closest lower bound to it from about 10 years ago, from a paper that is obtained by a different, related but not the same kind of method. So we can look at things like that. I know if in social sciences people care about these kind of consensus dynamics on random graphs, then this might be an interesting method to analyze some of those. I still have a few minutes to go back to the large degree limit and to the SK model. And I already told about some of these results to some of you because that's the paper we will be submitting soon and that I'm kind of thinking about. So still the same dynamics. Oh, okay, we will see which dynamics. Because if we keep the same dynamics and we go to the degree large, it actually goes to a 2-cycle. So we are not happy with that. This will not even go down in the energy and will keep oscillating. We don't want that. So which dynamics? So we get inspired by this paper by Giorgio Parisi. I mean, you know Giorgio Parisi for his work on spin glasses and maybe think about him as, you know, the amazing theoretician which he is, but you may not know that he is also an absolute computer programming geek. So he has a lot of kind of hobbies where he programs things, completely crazy things that you would not expect. And so he has papers, you know, every couple of years he posts a paper on the archive, doesn't send it anywhere, just on the archive. That is an essentially entirely numerical paper realizing something, and usually a single author because, you know, it's something he explored and he wouldn't bother, etc. So this is one of those papers. So he actually looks at these, look at the title, right? Large time zero temperature dynamics of the SK model. So that's the type of dynamics we are looking at. And he looks at 3 versions. So first of all, he updates the spin one by one. Not all at once, but one by one. And in 3 different orders. So either he takes a random order or sequential order. I mean, that makes essentially no difference. So let's say random order. Or he takes first those that are most unhappy. So he's very greedy. Or he takes first those that are unhappy but the least so. And he calls it reluctant. And he plots the performance. So this is just a picture from his paper. He plots the minus the energy. So above is lower energy. Below is higher energy. So we want to be lower energy. So above is more interesting. And look which of the algorithms is above. It's the reluctant one. Is the one that is flipping the spin that is the unsatisfied, but the least unsatisfied. So this was, 95. So 30 years ago, he went only to sizes 10, roughly 1,000. So this numerics is not very conclusive about where it goes. He says, okay, this goes somewhere, no, not to the ground state, but it's not like that. He also gives some, you know, solid arguments for that. So we did the numerics more properly, you know, gaining 30 years of Moore's law. This scales cubically, so we can go to 80,000, so a bit better, okay? Not that much. He was very good back then with the numerics. But we see the following thing. So what is plotted here is the energy that we get on average as a function of 1 over the size of the system. And on the y-axis is that energy subtracted from the ground state energy that we know the value up to 9 digits from Parisi's work. And then it's a log-log. Right? We take a log here and we take a log here. So in a plot like that, if you see a line that looks straight and goes down, it means that you're looking at a power law. And here, that's why I plot these dashed lines. This would be a power law which has an exponent minus half, and this would be a power law which has an exponent minus 0.6. And that line is somewhere in between. The ones above, they would have, you know, even if they may look as a line, the exponent is like minus 0.1, and you know, when it is so small as minus 0.1, it's more probably a log or not even going to 0. So those are not, you know, plausibly going to 0. And next slide is a more precise estimation where they go. But this one, the exponent is huge, minus half. I mean, this is going to 0. But that's right. So the conjecture is, based on the numerics, and it can be, of course, completely wrong, at some bigger size something else can happen, that this reluctant dynamics goes to the ground state density in the large n limit. Now, I discussed it with some of you these past days, and this is kind of curious, because if it is true, it means that somehow on the way, the dynamics must be picking the fact that the ground state is described using this ultrametric structure of the full RSB solution and all that. Like, how would that come up? I don't know. But it's a curious curious possibility. Here is where we extract actually estimates where it goes by looking at these lines and looking actually at the curvature at the end. Because if it's a paraboloid, it needs to be straight, so it cannot be bending up or down. And so we plot the curvature as the function of the energy that we would subtract. And when it crosses 0, that's kind of our estimate of what is the limiting energy. So for the random and greedy, we are somewhere at minus 0.728, something like that. But for the reluctant, the black line is the ground state, and the band is kind of our confidence on this kind of numerical estimation. So you see that we are extremely close to the ground state, and even looks like below, but that's actually, if we go to bigger size, we kind of check that this will go in the right direction. So this is just very consistent with going to the ground state. Curious thing. Can we analyze this? No. So far, the method that I told you, we can only analyze dynamics that are synchronous. And this one is sequential. I take one spin by one. And so then we were playing a bit with synchronous versions of the dynamics and analyzing it with the backtracking dynamical cavity method. But I see I'm almost at the end of my time. And let me just skip this. And if you're interested, I can show you later. So just a summary. With this backtracking dynamical cavity method, we can explicitly count structures of trajectories that go to a fixed point and their basin of attraction, and this gives us access to a lot of dynamical properties that before we did not have, because things kind of happen interestingly from the end of the dynamics and not from the beginning. And this is in particular useful for dynamical processes that are synchronous and rapid, such as quench in spin glasses, so not slow things. And this gives us some new results for the Sherrington-Kirkpatrick model that I presented. But maybe rather than summarizing what I told you, what are the conjectures that you can try to prove? So the first one, that the reluctant dynamics goes to the ground state, or refute. I mean, I would be happy with both, but this is curious. Analyze the random greedy dynamics or its variance and show where that one goes. And again, I learned that that's some ongoing work in the audience that is very exciting. You can establish the results obtained by the backtracking dynamical method, since these are essentially all the interesting cases in our self-consistency checks. Those are just given by any calculations, the type of proof of first and second moment, but on a quite complicated structure, so this will not be like one-page proof, at least not straightforwardly, but it can be done in the sense that there is no correlation that should be preventing the second moment method from not working. So for instance, the value of the consensus dynamical phase transition, we could have it more precisely and not only the bounds that exist. Or the kind of fourth point is that, as I was saying several times, a lot of this is completely blind to whether we are taking the ferromagnet at zero magnetization or the antiferromagnet or the spin glass case. And then the proof of this universality that we have in the paper of David is limited to the dense case and kind of to the particular counting that we were considering. But we believe that it's true in much broader generality. So trying to think about this maybe in some much bigger generality beyond specific cases, to me, that's a very interesting possibility. And I wanted to add with a thank you to my collaborators. Some time ago for a inaugural lecture at EPFL, I actually listed them all in one slide. So this is actually a year old, so the very last ones are not there. And highlighted the most common one, as I already said in the first lecture. I was asked at the dinner whether I know of a pair of collaborators that have more papers than we do. And David suggested that Jennifer Chase and Christian Borgs do, and I checked on Google Scholars, and indeed there are about 50 papers ahead of us. So we need to we need to work on it. So sorry.
But this will grow like a Moore's law, probably.
Okay. I will, no bonus. I will leave it here, and thank you all for coming for most of you, I think, the 3 lectures, and I hope you learn things and will work on some of them. I would be happy to hear from you if you actually do work on some of them and understand something more, and thank you.
Fascinating 3 lectures. Any questions? Any proofs? Maybe
In the meantime, that would be very impressive.
So I'm curious about this reluctant dynamic. So can you maybe, so I mean, it is one choice, right? You could have like a whole gradation between the most frustrated to the least frustrated, maybe do some random choice or something like. Was that some consensus towards which researchers have converged, or did it just pop up in this paper by Parisi and?
There is absolutely no consensus. I mean, we really found it like a year ago or so, and yeah, there is this bizarre, this paper by Parisi that Florent somehow remembered because at some point 10 years ago he was doing some simulations and used that trick to go to lower energies. Okay. Now, when I talked to some of my colleagues in computer science, right? In computer science, a lot of people study greedy dynamics not on random graphs, on generic graphs, and you can prove very interesting things about greedy procedures. And I was asking, do people commonly consider the kind of least greedy procedure? And to the people I talked to, it seemed surprising. Like they told me, I'm not really aware. If you are aware of papers where this type of least greedy dynamics is actually suggested or studied or brings something else, please let me know, because I am not aware of any, maybe one, but it's again some like forgotten paper on XORSAT by the physics community, so nothing kind of major in computer science. But if you have something in mind or somebody has, please let me know, because I wonder. Because from what some colleagues told me, this is actually pretty counterintuitive that this should go lower. So now that we studied it a bit, okay, we know that it needs bigger time to converge, quadratic as opposed to linear for the greedy ones. So it goes slower hence, and going slower, like the simulated annealing also goes slower, so that maybe helps. Is it restricted to this problem? Is it true for other problems that the reluctant one goes lower? I don't know. And as you are saying, this is just one choice, right? One could kind of make variants. Do the other variants also work? I do not know. It's probably yes, right? Probably we didn't kind of stumble on some really singular thing randomly. So probably it means that this problem is quite easy, that there are many dynamics that actually go to the ground state. But yeah, what's the status of this idea in kind of the landscape of heuristics in computer science? I wonder as well. And if you have some thoughts, write me a mail, or I'm happy to discuss it.
So I'm sorry if I'm asking the same question I asked earlier, but do you see did you do the experiments for dense graphs only, or dense and sparse, and do you see the similar results?
So we did for dense.
For sparse graphs, the dynamics translates into something like breaking the ties, which is indeed a very bizarre dynamic.
Yes,
Why would you start with breaking the ties and only then go to this?
Yeah, so
maybe breaking the ties is too much, because so in the sparse graphs you only have few discrete values of the field. So once you do something for all 0 ones, you do it for a big fraction of the graph. Breaking the ties is the type of thing that actually leads you very fast to a 2-cycle if you do it synchronously. If you do it sequentially, I don't know. We did not try much, because you would, on top of starting from small field, have to kind of choose which one of the 300 that have field 0 you actually pick first, so you would maybe do it random. It's a good question. I don't know. Yeah.
Small synchronous patches or something like that.
small what again?
Small synchronous patches.
Small synchronous patches.
Long fraction.
No.
why would you want to do that or be curious about that?
I'm wondering whether that should be similar to the sequential, passing one or other attribute.
Yeah, how would you choose the patches? You would, yeah, no, the short answer is no, but there was another question over there, yes.
I had a question on the transformer section of the talk.
Yes.
I think I'm still trying to understand why this sudden switch in the order around what happened between the semantic and the positional relations, and why does it even happen at the same point?
So they are actually the equations that we wrote, they are actually describing two local minima, or two minima. And what switches at that point is which one of them is global. So the curves that I had, I could have continued them, and they would continue. In one of the plots, you would not see kind of which one is lower. In the test error, you would also not see which one is lower. I would have to plot the train error to see which one is lower, which we also have in the equations, and that's how I decide which one I plot. So they stay there, but they switch. And what in a sense it means in the paper, I didn't cover it here, but in the paper we also have a little experiment that is still toy but less toy than what we do here. A simple task that we found when you have a sequence of numbers and at the output you look for the histogram. Okay, and now you can train a transformer on that task, and you can actually see that that if you run your Adam from different seeds, you actually sometimes find one type of fx point and other times another type of fx point that are quite different and correspond to a different algorithm for drawing a histogram from a sequence of numbers. Okay, so this actually does happen in kind of a less toy but still toy transformer, that you can actually, these are all kind of at least the synthetic tasks that people are trying such experiments on are, histogram, linear regression, some kind of modular arithmetic, something. You usually have different algorithms for those tasks, and indeed, the transformer can usually represent several of them, and depending on how you set up the training procedure, it can converge to one or the other. So we see that also in practice. So we expect that this is also happening in the model, but we kind of need to work out the training dynamics to see that, to which of the minimizers we are actually going.
Okay, let's give another round of applause for a great series.